in this model we have this anti-vibration mount, of course made of rubber. We decomposed this model into different parts, as you can see, but they are shared topology. So when we look at the mesh, there is node and element continuity. There is no any discontinuity here, which means that there is nothing wrong about decomposing this element this way. But the reason why we had to decompose this model this way, because we really need to be able to apply this multi-zone method that allows us a sweeps everywhere. So the logic of multi-zone is capturing the different areas on a model that are sweepable and apply the sweep, which was not possible because there is a certain degree of complexity in this model that we need to decompose it. So as we can see in this section, when we look at the inside inner elements, these bulk elements here, there is no any distorted elements. There is like sweeps everywhere. This is a very good thing for us to avoid those sometimes when some elements are very distorted. Even though bulk elements are not usually exposed to very high strains, but it may happen because of distortion, that though some artificial strains, very high artificial strains occur, which mistakes the fatigue results as well. Something that we really don't desire. This is just to mention why we have decomposed this model. Apart from the mesh, when we look down to the model, we do have boundary conditions here. Visibly, so we were able to solve this in 1 and 4 minutes, 1 hour and 4 minutes, and it's not a very long time. And this is the histories that the loading histories that we use it. So basically in y direction there is a dominating compression. It's more than dominating, it's like totally negative values that goes only downwards to compress the model in the xy direction, but in the minus y direction. But on x z directions we have negative and positive values, which in result, so when we look at the animation, how the model reacts to these loads, you can see that this is an exaggerated animation, but gives a hint about what are the loadings look like. But the question in this model is that we do have these load histories, but these are not the real load histories that we needed to apply as boundary conditions for this model. So let me show. So this is the real live load histories that we do have, which are composed of 1000 steps, 1000 time points. But here we had to run only a model for 64 time points. In order to get the histories for this one, the strain histories for this loading road load histories, we basically need to compute all these 1000 time points, which is going to be so expensive. Conversions problems and a lot of time consumed without really knowing if we in the end of the day were going to be able to solve it or no. So in order to do this, we use Endurica's EIE module. And the main topic of this tutorial is this module. So what the module says exactly, when you look at the real life loads, we use certain data acquisition equipment, and we capture frequency of 1000. This is like a typical frequency, and if the event duration is 30 minutes, the number of increments is going to be almost 2 million time increments that has to be computed. Very high time increment for a normal even very super powerful computers will really struggle to solve such histories. And of course this is for if our model is composed of 25,000 elements. This is like not very high, but it could be really higher than just 25,000, which will lead to a longer time analysis and a lot of time waste. When the problem is linear, there is this possibility to interpolate on X and Y, and you just pre-compute for a certain let's say 10% of the load histories, and interpolate linearly to get the histories for the strain histories for the rest of the data. But as the problem is nonlinear, we were dealing with rubbers. They are very hyperelastic, geometric nonlinearity, and material nonlinearity. So it's not easy. It's not possible to just interpolate simply. That's why we need EIE, which stands for efficient interpolation engine, that allows us to do this interpolation with accounting also for nonlinear phenomena. So the typical workflow for running an EIE job, or a typical workflow for a project that includes EIE job, it looks like this. So basically we need an FEA model, and we need to do material characterization, get our hyperelastic and crack growth low data and properties, and of course we need to have a road load data in a certain CSV file or whatever, and we need also to build a map over this road load. We are going to use not the road load for our FEA model. We will use the map that was derived, that was calculated from the road load using certain way that we're going to have a look later on the later slides. So we do have for our FEA model, what we do, we compute normally using the map road load histories, we get our strain histories, and we switch to EIE, and we feed our EIE the strain histories that we pre-computed on this model, and also the map and the road load. So in the end we get strain histories for this road load that we will use in CL module to solve and get our fatigue life based not on this road load but based on this original road load, to see what are the critical elements and what are the critical areas when the model is subjected to such a road load. Options that EIE provide for data treatments, among which we do have channel reduction here. When we have so many channels, when we have, for example, displacements in X and Y and Z, which makes 3 channels, and rotations also in X and Y and Z, it is sometimes useful to reduce the number of channels from 6 to 5 or from 6 to 4. So every channel reduction is punished when we do a very big reduction, so the error is going to be bigger. So we have to keep the error acceptable. The other option that EIE provides is the pathfinder. We will extract a map from that road load. In order to do that, so we have this pathfinder that provides this option. Once we get used pathfinder and get our map, so we have all the ingredients to run our model on EIE and get our model fatigue life results sorted out. But what we need to do a data reduction is the original road load data in a CSV format. And if we open a command prompt here and say EIE-H, so we get all the code lines that we need for every option. For example, for Pathfinder we have this code lines. For dimension reduction we have these code lines, and in order also to, sometimes when we have a file in RPC format and we want to convert it to CSV, of course we have other ways, but if in case that we want also to use EIE, so it is possible. So in this case we want to reduce data, we want to reduce dimension, we want to reduce channel number. So we're going to use this code line. We copy this because we say EIE dimension reduction, and so we paste it here, space, we have to input the file name here, which is road load. We copy the file name here from here, paste it here, and space, so dimension reduction, -d target dimension, -d space, the number of dimensions of the original data is 3, so we want to convert it to a 2 dimension. So what we do, we say 2 and we click enter. So we got successfully checked our license. We get error dimension reduction program, unable to open Oh, yeah. So we need to add the extension here and see if the error will still exist or will be solved. Yeah, now we are able to get it done. So this job is done. It's a short one, and these are the results. We get a file that contains how much the error is for this reduction. We get the 2D reduction channel. We get the original, yeah. We get this the transform matrix. So if we open this file, we're going to see that the reduction has done from 3 channels to 2. So this is concerning the data channel, the data reduction. And for the Pathfinder, we also have the same original file here that we will create a command prompt here and get these. We copy this. So EIE Pathfinder, paste it here. So we don't really have to specify all these details. If we just this is of course mandatory. We need to input the file name, so -e root, I think it's root load.csv, and we specify also this is a transform, this is a total number of points. Yeah, so total number of points is what I'm going to specify. From 1000 time points, I want to reduce it to 64. So I say here 64. Sorry, I say -p space 64, and I click, and I get it done in a very short time. So this is the Pathfinder result. This is the map that we've been talking about, a map that is composed of 64 points. This same map that we copy paste here in our FEA model as displacement data in order to solve and get these strain histories. When we look at the result of the Pathfinder, it is not necessary, but it is a good visualization way to plot these data in a 3-dimensional plot using Python or MATLAB, whatever. We just need to paste. So we just need to use pandas and matplotlib modules, and just give the path and specify that there is no header, and we get something like this. This is the original data, and this is the map data. This is just for the sake of visualization. If we skip this, that's all fine, that's all right. Sometimes it's good to visualize just to make sure that somehow this map is a reflection of something like this, because we may get something that has nothing to do with this original data. In this case, we realize that the Pathfinder operation was not done quite properly, or maybe the number of points that we specified for the map maybe is very small enough to do not really reflect this load histories. When we look at the ingredients that we need for a project that includes EIE, we definitely need Endurica input file. So I'm going back to my model here. So we need something like this input file that contains outputs, what kind of outputs that we want to post-process and explore after the fatigue analysis calculations are done. The file has to contain the precursor size, the initial and final precursor size. It has to contain the hyperelastic properties and the crack growth low. That's all we need to have as information in our input file. We need an FEA model. So for this one we need Endurica, of course, license. And the Endurica license that we have, it should include EIE and CL. For the FEA model we need, of course, Ansys license, and we need our original data road load that we may get from automotive manufacturer or from the internet, from literature or from whatever, depending on the situation. Of course, in some workflows we may use Python really to be very important part of the workflow, where some calculations are done, some data treatments are done on Python and are part of the workflow. But in this case, Python is not used as part of the workflow, it's just used for visualization. That's why it's just optional. When we look at this actual model, it is important to specify that I'm running this model in a very simple machine. I don't have like a very super powerful computer that allowed me to get strain histories for load histories composing 1000 time points. Look at the processor and the CPU core number. So it's like not a weak computer, but it's not powerful. It's not even powerful. So and the model, some information about our FEA model. We have the node number. It's not a very big number, not very fine mesh. The element order is linear. I don't prefer linear for hyperelastic materials, because quadratic are much more capable of capturing strains over like complicated shapes, which you can see here. It's a solid 185, and time step is 46, and the total CPU solve time is 2722. It's like around 1 second, 1 hour. These are the signals that we use it for our FEA model. In X, it goes from -1.5 to +1.5 up and down. In Z is the same, but in X it goes from 0 to 1.6 millimeter, but all the values are negative. When we are done and we have our strain histories, we go and export those data, those histories, as we have done before in the previous tutorial. But there is something that has to be reminded. If we have 64 here as time point, our strain histories has to compose also 64 time. So every strain represents one time point. Because we are going to treat this data in EIE, we don't need to do this in a normal CL or DT job, but as it is EIE, most of times we get a lot of errors in EIE just because of this. So that's why we need to specify this in Ansys. So we go to analysis settings, go to output control, and we come to store results at we choose equally spaced points option, and we specify a value of 64. This way, when we do this, so we're able to get other time frames according to which strain histories are going to be exported. So the number here is 64, which we really need to get. If we didn't do this here, we wouldn't be able to get this 64 number here. That's what I wanted to say. So we choose, we pick up this resource set entirely, including the elements set entirely, and we specify our export file to the directory where our input file is located. So it's in the mesh EIE transmission mount, this one. Say yes, and then we switch to history. We choose the bulk 3D model. Hydrostatic pressure has to be also included. The period here is 64, right? The total period is 64, and that's all we need to include as information. We click on export, and it may take some time to get the export operation done. Now that the export operation has finished, click OK and close this window and go to see what did we get here. So what we get here is a KI file that contains our strain histories and all the path where the KI file is appended. Now that we got our KI file, it's probably time to run the EIE module. So we go into run the EIE from the same folder as a command prompt. Without Endurica. So a new project, we're going to open a new project and specify the directory to the same folder where we have our KI input and model files, which is EIE mount 2. Name it. So we name it EIE tuto. and we save it. So once we save it, our EIE project, we have a couple windows here where we need to input certain data. This window and this tab where it is written definition, we have this channel definition. We need 3 channels because we have a 3-dimensional displacement, so it's like combination of X, Y and Z displacement signals. That's why we need 3 channels. And then we add the map that corresponds to that data here. Say add, and we look for the file that contains the map. As we have created the map using the Pathfinder, we're going to look for the Pathfinder folder and select this road load path. Say open and move to the branch. We can see that our data is exposed here, it's plotted here, 3 signals X, Y and Z, and there is nothing to change here. Go to source. So in this window we need to import our strain histories for this map. That's why we're going to find the file that contains those strain histories. As we have exported those strain histories to the same folder where the model was run, our KI file is here, .ki. We select it, we open, and we're all set for the map and for the source branch and definition. Now we move to histories. At this stage we are required to import our full road load data. So in order to do that, we go add. I have this defaultly named history -1. We double click and we change the name of this history to, let's say, root load data. Let's say data, okay. And here we have a file, not a table, and we go browse to the directory where we have saved our original data. At the data treatment folder there is this original dat where we do have our original data saved. So we're all set here. Go back here and we have our original data. As you can see here, 1000 time points, and then there is nothing else to do here. That's all we need to do. So we go to create a job, so you say add, double click, change the name of this job from default to EIE to tow. I don't know, say mount, and for the history, so there is only one history, so it is by default selected. History database. This is the other ones if we use the older versions of Endurica, so we're going to pick up this output directory. We select where the strain histories are going to be saved, because we are going to calculate strain histories for the original road load data, which is going to be at the same folder where we have solved this model. Let's say here select folder. we use just one thread. So in case we have a multi-thread Endurica license, we have this possibility to use up to the maximum number allowed for your machines. So in this machine my maximum thread number is 8, so I have the right to select 8 here in order to run this model faster. I'm not sure if my license is multi-thread, so my model is not very big, so I'm good with 1. I of course have to select the strain histories and hydrostatic stress. So I'm all set here. Now I am ready to just submit this job and to wait for the results to get started. Okay, so we may have a problem here. There is an error message that comes. It's always good to read the error message, this window that opens automatically when we run the EIE, because we have more details about the error. So the error says is in initialize job there are more data frame in the source file. So in this file here, it says in my KI file here, in the source file, then there are in the branch definition. So the branch definition is here, this one. So this one. So this data was generated from these boundary conditions that I think that this is the error. So when we look at the boundary conditions here, it starts with 0, but I believe that my map file doesn't start with 0. That's what I'm going to double check. So Pathfinder, go to the map, which is the road load path, and see if this starts with it doesn't start with 0 here, but the boundary conditions here start with 0, which makes the KI file frame bigger, as they say. It says the error here that the source data frame in the source is bigger than the data frame it is in the branch definition, which is the map. That's visual here. As you can see, visible here, there is this extra row here, and by consequence the the strain histories are going to record 0 strains for these 0 displacements, which is like one step bigger than this one here that starts from this data, not from 0. I'm going to insert a row, and of course the first 3, like the first cells are going to contain a 0 value. I save this and I close it. I go back to my branch definition here. I remove this and I replace it with the one that we have just edited, and that's the only thing that we have to change, and we submit again to see if the problem has already disappeared. Yeah, it is initialized. I think that there is progress. It's running. There is progress, and I think we're good now. It is solving. So, and it is completed. It is completed now. Once we have this calculations, EIE calculations are done. We go to our directory and see what is the result of this calculation that we just did in EIE. So the result is an auto KI file. So here is the very first KI file that we got from the map as boundary condition, as loading histories. Here is the KI file that also contains, as you can see, is a way bigger, like 10 times bigger than the one that we generated from the map. And the reason why it is bigger, because these constraint histories are generated from a 1000 time points load histories, and this one was generated from only 64 time increments. This is the difference. Now what we do is that we run our Endurica job. This is a complete file that has almost everything to be run, but in just the only thing that we change is that we don't want to account for these train histories while running this Endurica job, CL job. We account for this bigger file and see what the result is going to be. So I'm quite sure that it's going to take a lot of time before we get the results. So I'm saving this, I'm closing this, and I create a command prompt and I say Endurica. So this file starts with E, so I look for everything that starts with E. Sorry, I'm running this, so something starts with T, and this is it. So I'm all good now to run this and see what is going to be the result. This is going to take a lot of time, maybe 1 hour or something. And now the CL calculations have been completed. Element number 23501, which is the most critical, with something like 9.4 E5 as a fatigue life, which is almost 1 million cycles, which is kinda at the limit of infinite life, but it could be critical, and the plane number is 4. What we do now is that after these calculations have been completed, there is this file that is generated, which is the output file. We'll go to our FEA model and we import the EKO file. I look at the destination as this one and I say open. Now I do evaluate all the results. So after importing this KO file, we get these results here, and the most critical areas after this model is subjected to that original long road load loadings is going to be this area here, the surroundings of this upper face. And if we want to explore the most critical element. So we're gonna copy this element here and paste it here just to see what kind. So what is the element? So the element is this one here. The crack is going to be initiated at this element on a certain plane called plane number 4. So if we want to know what are the coordinates of this plane number 4, we need to open this scale file and look for the planes and look for the plane number 4. See what are the coordinates of this plane. Or we have also the possibility to visualize the critical plane sphere on the Endurica viewer. So these are the plane ID. It says ID numbers here. So this one, I believe, should be the one that we have Cartesian coordinates here. We just copy paste these coordinates in X, Y, and Z to know in which plane this crack is going to be progressing over this critical element. So mostly this is all for EIE. We tried to cover almost every aspect needed for this topic. I hope that it was useful for your projects and it was informative and insightful.